Hello. Hi guys, good morning and welcome back to the new video. Firstly, apologies for not being a regular lately, but from now I will be for sure regular. Medium and hard questions will be coming in. I will not pick up easy questions. Only the medium and the hard questions will be coming in for sure regular. Cool. Let's quickly jump into the question. It's super easy. I swear. The video will be short and super simple and easy. Cool. The problem just says that okay, I have a frog crossing a river and the river is divided into some number of units, and basically at each unit I can have some of these stones. Now frog can only jump on these stones. He cannot jump or dive into the water. Now I have a list of stones, positive like positions, which means stones are just the positions. I'm just having the positions, and if I'm having a position, which means I have a stone at that position. Cool. And it is sorted in the ascending order. Cool. That's a thing for us. Now I have to determine if the frog can cross the river by landing on last stone. So basically, frog has some stones with him. He will start from the first stone. He will keep on jumping and he can jump only on these stones, and he has to reach the last stone. Now initially the frog is on the first stone. As for sure, he will start from the first stone itself and assumes that the first jump must be 1 unit. And also, if you look at the constraints, he is saying that the first stone is always a stone 0, and also the first jump is of size 1, which means after the first jump, the frog should for sure land onto location 1. And the location 1 is not there, which means the stone at 1 is not there, which means the frog will not even reach at the last position. So we have two major things. Okay, the first jump is of a size 1, and also the frog is starting from the stone 0, which means the location 0. Now, if the frog's last jump was k units. Now, okay, this all jumping stuff was good, but how is this jumping stuff is going to propagate? As in, like, if I do some jump, then how to do the next jump? That is told by this condition, that if I had a last jump of k units, the next jump, it can be of k minus 1, k or k plus 1 units. Now, here is the big hint. Now, see, we are just reading the questions out. Now, while reading the question out, we will actually see, oh, what algorithm? Because for sure, it's a problem of data structure algorithm. So, meanwhile, while reading the question itself, we will figure out what algorithm is going to be needed in this problem. And as we can easily see, and we have easily seen in our previous discussions also, if you have not followed us, follow to have more such questions. But meanwhile, if you have not seen that, it's a very standard question. Okay, for one thing, I have 3 more options to follow up. For k, I can have k minus 1, k and k plus 1 units. Now the frog can only jump in the forward direction, which means okay, I have a frog if the k is, let's say, xyz, so I can do the next jump as xyz minus 1, xyz and xyz plus 1, which means if I have the last jump as 4, the next jump I can do is either a 3 or a 4 or a 5. Now the next jump I can do from this 3 is 2, 3 or 4. From this 4 I can do a 3, 4 or 5. From this 5 I can do a 4, 5 or 6. Now considering all of these are, you can easily see that I have some repeating sub problems. I will again, from this location, I will again do a jump of 3. You can also see a jump of 3. From here I can do a jump of 4. Okay, a jump of 4, a jump of 4. I can do a jump of 5, a jump of 5. You saw, although from the problem statement itself, from one option, if we are spawning 3 options, there's a high chance these options can overlap. And as we are spawning some options, we know that okay, we can do it either recursive or we can do it iterative. But for sure, we know that we have to memorize our stuff, or basically we have to keep stored in the array, let's say DP or anything like that, so as to know that we don't compute it again and again. So with this thing, by reading the question itself, we know that okay, DP is going to be applied because we know that we have a repeating subproblem part. Now we know that how last jump is I'm more concerned of. So if I just ask you, now you know that we will apply DP for sure, but as you know, I know that in DP we should know okay, what is the state like, and how we determine the state is just by saying okay, what all conditions I need the most. And as in any problem of DP, one thing is for sure needed is the index, or basically if I'm iterating on, let's say, stones, positions, anything whatsoever. So I will be going and iterating on all these locations, right? So for sure I will be needing the positions at, or mean like the indexes or maybe the values of these particular stones, right? Maybe it can be values, it can be locations, it can be position, anything, but I should be going on to every stone. So one thing is for sure, what we need, we need, okay, at what index, and I'm not saying, okay, only index, it can be the stone itself, which means I will go on to every stone, or I can go to every index, anything whatsoever. So I should be knowing what index I am at, because I will go on to every index from left to right. But I should also know what was the last jump, because on the basis of the last jump itself, I will be going on to the next future jump. So I should be also knowing what was the last jump to know what is the next jump, because next jump, it can be k minus 1, k and k plus 1. And with this next jump, I can land on to next position, which means next stone. I'm not saying the next index, I'm saying the next stone, which means at, and while with the example itself, we will see what is the next stone, what's the next index. But at index I can have a stone, let's say 14, which means I have a stone at the position 14. Index is 5, and let's say the index 6, I have the stone at location, let's say 18. So that is, I'm saying, okay, next stone, which means, okay, what is the next stone which I'm landing at? So with this, and these to look the most major stuff which we can use in the problem. Now okay, we have understood the major crux, and we have got the entire intuition. Okay, I will apply DP, I will try to use my last jump, I will try to use the indexes. Now we will walk through the example itself to actually apply that in our problem and see that how we can actually solve it. So we have all these stones. Now when I say stones, it means the location at these, which means a stone at location 0, a stone at location 1, a stone at location 3, or you can say position also. Now as we saw, the first stone is at location 0, and for sure the first jump was of 1 units. So after doing the 1 units, it will land to 1. But we need to store for 1 what is actually the last jump it had. Now if we land onto 1, see why we need to store, because for next time when from 1 I'm gonna jump to next location, I need to know what was the last jump, so that I should know what is the next jump it should have. Cool. So we know that, okay, for the first stone, which means the stone at position 1, we have the last jump as 1. So I can store that with him, because I need to store the last jumps as we discussed above also. But now, okay, if we have for position 1, I have the last jump size as 1. What can be the next jump size? It can be k minus 1, k and k plus 1. Now if I do a k minus 1, I got a 0. Which means my next jump size is 0. If I am at 1, my next jump size is 0, I will still remain at 1. So I would not go at that location again. That is obvious, okay. If I do a size 1 jump, which means from 1, I will do a 1 size jump, I will reach to a 2. Oh, good. From 1, I can do a jump of size 2. I can reach a location of size 3. Sorry, I can reach the position 3. Now, position 3, I can see I have position 3, which means I have a stone at position 3, but at position 2, I don't see here, which means I have water at position 2. Oh, water at position 2. But for position 3, I can land on to position 3 by doing a jump of size 2 from 1. But for position 3, I am concerned about the last jump. So considering I jumped from 1 to 3, but last jump which he did was of 2. So for 3, I am concerned about the jump. For 1, I was concerned about the jump, which was 1. For 3 also, I am concerned about the jump, which is 2. So I'll store that. Cool. Done. Now, from 3, I'm going to jump to whatsoever locations I can jump on. But you know that I have also maintained the last jump, because it was given the question itself that you need to maintain the last jump, and with the last jump itself, you can just go and do a k minus 1, k and k plus 1 jumps. Now, coming on back, that we were at 3, I can do the next jump as either 1, 2 or 3. If I do a jump of size 1, from 3 it can reach to 4. Okay, 4. From 2 of size 2, I can reach a 5 or 6. Now, I cannot see 4, which means 4 location water was there. But at 5 and 6, I have stones. Cool. For 6, I know the last jump it did was of size 3. Cool. Put it there, because I need the last jump for it. For 5, I also know, okay, last jump was of size 2. Now, Aryan, you are storing this thing in which data structure? No worries. Don't worry. It can be array, vector, hash set, map, anything. Let's imagine. But you know one thing for sure. For every stone, I'm not saying the position. For every stone, again, I'm not saying the position. For every stone, which means these, I'm not saying the indexes. I'm not saying the indexes. For every stone, which means 3, 5, 6, you are storing what was the last possible, what were the last jumps, sizes it had, which means you will need to maintain a map where the key is actually this stone, and the value will be some data structure. We will see what that data structure is, but meanwhile just remember it will be a map from the stone, which means this, it is actually a position or the location where the stone is there, to a data structure where it will have the jump sizes. But I know that we need to see what data structure we're gonna use, but indirectly we know something like this is gonna happen. Now coming on back, we had reached 5 and 6, but we have to go on from 5 because we are going from left to right. So we'll see 5, last jump of size was 2, cool. So next jump size, it can be 1, 2 or 3. Next location, it can be 6, 7 and 8. 7 not even in my entire stones array, cool, so it is not there. 6 I can go, okay, 6 I can go of size 1, okay. I added earlier, it was 3 only, you remembered, from 3, but from 5 also I can reach 6, but the last jump is 1. So 6 has 2 last jumps now, 1 and 3. 1 and 3, cool. From 8 I can reach again of jump size 3. Now again, as we land on to 6, I have jump sizes 3 and 1. So for this 3, it can have 2, 3 and 4 as new jump sizes. For 1, it can have 0, 1 and 2 as new jump sizes. For this 2, I can have 8, 9 and 10 as the new locations. For this, it can have, for sure, if I do a jump size of 0, it will still remain there. So either you can put a 6 or still you can either say, okay, just go on to 7 and 8. Now 7, 9 and 10 are not even in my stones array, so for sure ignore that. 8 I have it, so I can reach 8 with the jump size of 2, okay, jump size of 2. But I can again, it is again saying reach 8 with a jump size of 2. So shall I add a 2 again? No, I just need the jump sizes, because both the 2s will give me the next jump sizes as same. So which means I could actually, if I put this data structure, if this data structure is not unique, I might actually repeat my jump sizes. So I will try to make this data structure as unique. So what I can have is, I can have an unordered map, so that I can have an unordered set, so that this jump sizes in my next location, which means in this next stone, the jump sizes will always be unique. It will be 2 and 3, so that next 2 even if comes in, it will still remain 2 and 3 only. Now okay, for 8 my next locations are, my last jump sizes are 2 and 3. Again, this data structure we have known it is a set, but we know it can also be an unordered set because we don't want to increase the complexity part. Again, for this, for 2, next jump sizes are 1, 2 and 3. For 3, it is 2, 3 and 4. Next locations are 9, 10 and 11. It is 10, 11 and 12. These are not there. I have only 12, so I can say for location 12, the jump size, last jump size was actually a 4. Cool. Now I'll go on to my 4, which means I'll look on to location 12. Here the jump size is 4. New locations are 3, 4 and 5. Cool. I'll get the next location as 15, 16 and 17. Now 15, 16 is not even there. 17 I have, and YOLO. I can say, okay, for you the previous jump location is 15. Now you can go forward, but as we have reached the end, we will not go forward. Now with this, in the end you will check for the last location, which means for the last stone, were you able to have something in its entire set? If you have, which means you were able to reach the last location, and if it is the case, simply return a true. So now you will keep the map from stone of I. I'm saying this, I'm not saying the indexes, I'm not saying from I, I'm saying from stone of I. Why I and why not I? You only want this data structure, right, at this location. But you also saw that as soon as I will find the next jump locations, I will go the next location itself, which means I have found the next jump size. I'll also find the next location. For this next location, which means I have to map for 17, I have to map a number as 5, which means I will push, okay, map of 17, I need to push 5 in its data structure, which means here it is a set. So I can insert that element 5 in its data structure. So Although I can just say, okay, I will find the location of 17, which is the index, let's say this, which is let's say 6, then I will just push in that index. That's not required at all. You can simply use the stones itself, which means you can use the stone of I to map with the set of jump sizes. Why set? Because I got to know that, okay, it can be repeating and I don't want that repeating jump sizes. That is the main crux. You will go on from left, right. I will use a DP or basically a memorization so as to know I am landing on and don't repeating the stuff again. I will use a map and that would be done. Let's quickly see the code. It's pretty simple, exactly very easy. Firstly, that while if I do the first jump, I will start from 0. I have to land onto 1. So for 1, the previous jump size will actually be a 1, and that we saw that is actually in the question itself. Now I can start on from the index 1 up till the end, because I will go on to every of these stones from left to right. I will see for this particular stones what all jump sizes it had to go on to the next stone. As you saw, for any stone, I was iterating on all of the jump sizes it had, and with this iterating, I'll go on to every of these 3 stones. With this, I will find every of the new locations, and if I found a new location, I will just simply do a map of that new location. Cool. I will go on to every of those jump sizes for that particular stone, which is the stone of I. With that, I know, okay, current stone of I is this. If the new jump is the jump size, I am iterating on all the jump sizes, right? If the current jump size is this, so it will be the new location. For this new location, I need to push in the last jump size, which is the current jump size. So for this new location, with this ith index, the current jump size is this. So for the next location, which is the stones of I plus jump size, the last jump size will be this particular jump size given by the ith index itself. So ith index is giving the jump size to its next values. And same I will do on with +1 and -1 also, because we have 3 conditions. It is k plus 1, k minus 1 and k. Right, now same I will do. I'll keep on inserting, and that is actually a memorization stuff happening. Or basically I'm actually here itself, because see, I just wanted to store some values, and I'm using my map. I have not named it as a DP itself. You can name this as a DP itself, no worries at all, but simply it is just DP is indirectly saying, okay, I am just not repeating that same stuff again. I am using my memory power to actually store that in my memory, and by this I will iterate on to all such of my indexes from 1 to n. And at last, if I was able to say for my any stones, if I was able to reach my last stone, which means my last stone would be having some value in its set, okay, which means I was able to reach it. If it is 0, oh, I was not able to reach it. If it is not 0, which means I was able to reach it, so simply return a true, and that's how you can simply solve it. Now time and space is roughly O of n. Again, I'm saying roughly. In worst case, it can be O of n square, but still it is not exactly O of n square. It is less than O of n square, but still it is touching O of n square. How? If we simply say the worst case, it can be that in our entire stuff, everything, okay, for how O of n square can happen, I have n stones. For every stone, I should have n, right? But I know that if I just ask you what is the sum of n natural numbers, 1, 2, 3, 4, 5, 6, it will be n into n plus 1 by 2, right? So even if I have 1, 2, 3, 4, 5, 6, so it will be n into n plus 1 by 2, which is roughly a n square thing. Now coming on back, what is this? Now I have showed you this formula so as to just relate you that, okay, it is increasing like this. If it is increasing like this, which means that it can be O of n square. Remember that roughly. Again, Aryan, how it is increasing? For if you just write all these, now what you want is maximize this entire length, right? It is 0, it is 1, it is 1. So I just wanted to kind of roughly, if I want to prove its complexity, so I just roughly want to like maximize it, like worst case possible. So I just have it 0, 1, 2, 3. Like it was my intention, 4, 5, 6, like this, so that it keeps on increasing, and I can simply say, okay, it is O of n into n plus 1 by 2. Now, if this is the case, so I will try to prove it, but I could see, okay, I am just plotting the next, like the jump sizes which I will have. Okay, it is a set one size, it's a two size, it's a two size, it's a three size, again it's a three size. So you will see it's a pattern. Okay, I will have a 0. Okay, I will have a 1 sorry, I will have 1 I will have a 2 again. For this I will have a 3 and it will keep on going. It will be a 4. Now you saw it is kind of, it is not exactly 1 plus 2 plus 3 plus 4. It is not like that. It is actually a 1 plus 1 plus 2 plus 2 plus 2 plus 3 plus 3 plus 3 plus 3 plus 4 plus 4 plus 4 plus 4 plus 4 5 times. Now you saw there's a pattern in this. So by this pattern itself you can prove the complexity, but roughly if I just imagine, okay, increase it and make it as 1 plus 2 plus 3 plus 4 plus 5, I can easily see that, okay, it is actually a n into n plus 1 by 2, or roughly O of n square. Now that is see, again I'm saying it will be less than that, but still it is roughly touching that point. So we can easily say, okay, the time complexity of space complexity is O of n square. If you still want to prove it, you can instead of taking the map, you can take a array also. That is also possible, but this is the most shortest and easiest code to actually explain and understand. That's the reason I just showed you this, and it's more intuitive also. Cool. That was it. Code is down below. I hope that you guys liked it. Say no, goodbye, take care, bye bye.